Hi, in this lesson we will study the A-star algorithm. It is another optimization of the Dijkstra's algorithm for the case when you have a specific source and specific target, and at any point you have an estimation of how long does it take to get from this point to the target. This estimation doesn't have to be exactly precise, but if it is good enough, it can speed up your search a lot. An example of such estimation is very simple. If you have the coordinates of your target point and you have a phone with GPS controller and you know the GPS coordinates of your current point, you can have an estimation based on the distance by the straight line between those 2 points and the speed of your car. So this is the kind of information we can use to greatly improve the performance of the Dijkstra's algorithm. So let's first understand the notion of the directed search. And to accomplish directed search, we will need the notion of potential function. So we can take any function mapping vertices to real numbers, and it will be called a potential function. And then the value of this potential function on a vertex is called this vertex's potential. So this potential function defines new edge weights. If we had edge weight L of uv on the initial graph, then we can denote by L pi of uv the new edge weight, which is equal to the old edge weight minus the potential of the starting vertex plus the potential of the ending vertex of that edge. And it turns out that if we replace the old edge weights with these new edge weights, it doesn't change the shortest paths. Well, of course, it does change the distances between vertices. What I'm saying is only that the paths themselves, which were shortest in the initial graph, they are also the shortest paths between the same pair of vertices in the new graph, and vice versa. The shortest paths in the new graph with new edge weights are also the shortest path between the same pair of vertices in the initial graph. And to prove this, I need this lemma. For any potential function mapping vertices to the real numbers, for any two fixed vertices s and t in the graph and any path p between them, the length of this path in the new graph with new edge weights is equal to the length of this path in the initial graph minus the potential of the starting vertex and plus the potential of the ending vertex. Why is this important? Well, because if you fix the starting and ending vertex, then for any path, its length in the initial graph and its length in the new graph differ by a constant, because this constant only depends on the starting vertex and the ending vertex, and we fix them. And so if some path was the shortest path between s and t, then it will stay the shortest path between s and t in the new graph, because all the paths just add a constant to their length, and so the paths which were shorter than others, they stay shorter than others. And the same goes vice versa. If the path was shortest in the new graph, it was also shortest in the initial graph. And now let's prove this lemma. We consider some particular path p from s to t, and we also denote s as v1 and t as vk, and the intermediate vertices v2, v3, and so on, vk minus 1 are the vertices of this path. And now we consider the length of this path in the new graph with the new edge weights. By definition, it is equal to the sum of the length of the edges of this path, which is L pi of v1 to v2 plus L pi of v2 to v3 and so on. And then we can rewrite each L pi from vi to vi plus 1 by definition. And we know that L pi of v1 to v2 is equal to L of v1 to v2 minus the potential of v1 plus the potential of v2. So this first line is equal to L pi of v1 to v2. And each of the next lines is similar. It corresponds to the length of the edge in the new graph with the new edge weights. So we write each edge on its own line, and now we can notice that there are summands which cancel out. For example, pi of v2 here and pi of v2 here are with different signs, so they cancel out. And the same will happen with pi of v3 and pi of v3 here. And the same will happen with pi of vk minus 1 and minus pi of vk minus 1. So most of the terms, including this pi of vk minus 2, will cancel out. The only thing that is left is the sum of the length of the initial edges minus the first potential of the starting vertex minus pi of v1 and plus pi of vk, the last vertex. Those are the only two summands of the form pi of something which don't cancel out. And then we can rewrite this as the first summand is the length of this path in the initial graph, L of p, minus the potential of the starting vertex, because v1 is the same as s, and plus the potential of the last vertex, and vk is the same as t. So the length of the path in the new graph is equal to the length of the path in the initial graph minus the potential of the starting vertex plus the potential of the target vertex. So we've proved our lemma, and so we know that the shortest paths in the initial graph and in the new graph with new edge weights are the same, although their lengths differ by some constant depending on the starting and ending vertex of the path. Now we can formulate an algorithm which can be called Dijkstra with potentials. So we take some potential function pi and we'll launch the Dijkstra algorithm with new edge weights L pi instead of the initial edge weights L. And the resulting shortest path is also a shortest path in the initial graph. So the result of this algorithm is the same as the result of the initial Dijkstra's algorithm. But depending on the potential function pi, maybe it will come from the source vertex S to the target vertex T faster than with the initial edge weights, because the order of vertices that this algorithm considers can be different. So this is the idea of optimization. But does any potential function fit us in this case if we want to run Dijkstra's algorithm using the new edge weights? Well, the answer is no, because for any edge from u to v, the new length L pi of uv must be non-negative so that we can apply Dijkstra's algorithm for these edge weights. So such potential function for which this is true, that all the new edge lengths will be non-negative, is called feasible. Now the intuition behind the potential function is the following. Pi of v is going to be an estimation of the distance from the current vertex v to the target vertex t. So how far is it from here to t? If we have such estimation, we can often avoid going into wrong direction, and that's why we'll get a directed search. And typically in practice, pi of v is a lower bound on the distance from the current point to the target. For example, on a real map, a path from the current point to the target cannot be shorter than if we manage to go directly on a straight line from the current point to the target. This is often not possible because of houses or mountains, but if this is possible, this is the shortest path possible at all, and our real path cannot be shorter than the straight line segment between the current point and the end point. So A-star algorithm is basically this Dijkstra with potentials. So what does Dijkstra with potentials do? It goes in iterations, and on each iteration it picks the vertex v which minimizes the current estimate of distance to v. And what will it be equal to? We know that any path in the new graph differs from the same path in the old graph by minus potential of the starting vertex plus potential of the ending vertex. So we are going to pick v minimizing dist of v, which is the distance estimate if we ran the regular Dijkstra's algorithm on the same graph, which is basically the length of the best known path from the source vertex to v, minus pi of s plus pi of v. Now notice that pi of s summand is the same for all v. So the vertex v which minimizes this expression is the same v that minimizes just dist of v plus pi of v. And in some sense, this is basically the most promising vertex, because pi of v is an estimate of the distance from v to the target. And so we picked vertex v with the minimum current estimate of the distance from source vertex to v plus the distance from V to the target vertex. And this is in turn an estimation of the shortest path from S to T going through V. So this is why the search is directed. We always go not just to the closest vertex to S, which is still not unprocessed, but we also want it to be close enough to the target. And this is why, while we're searching, we avoid going away directly from the target. And then as soon as we find the vertex T as the vertex minimizing this expression in the Dijkstra's algorithm on this new graph, we stop. So, of course, this algorithm could still go through the whole graph before it gets to the target. But in practice, if we have a good estimate of the distance left from the current point to the target, we will get to the target and extract it much earlier. And on the way there, we will avoid a lot of turns in the wrong direction.